These are Algebra 2 notes, 8.3 graph general rational functions. So rational functions at their most general form are going to be a polynomial. In this case, we've chosen to represent that with a p of x in the numerator and a q of x in the denominator. So you can see this is a general polynomial where your first coefficient is sub m, and then you have x raised to the mth power, and that goes all the way down to a constant at the end. So these are just general polynomials. Recall from 8.2, we did graph some rational functions already. We graphed rational functions where we had a constant in the numerator, like maybe a 3, and then it would be over an x by itself, or sometimes x plus a number or minus a number, and we could even have a constant outside. So let's do a 4, so we have different numbers. We also practiced with rational functions that were something like x plus 2 over x minus 3. So we had something linear in the top and bottom. I think I'm going to get rid of the minus 4 too for what we're working on right now. So I am going to be referring back to the rational functions that we already know here, just to kind of help you understand the new rational functions that we're looking at. So we're looking at more general rational functions. So now we could have a quadratic in the numerator denominator. We could even have a higher degree polynomial. But at this point, when we're talking about general rational functions, we're saying anything goes. So we still have our x-intercepts as the real zeros of p of x. So p of x is our numerator, so that still means we get x-intercepts from having our numerator equal 0. So we're taking this language from the textbook and we're just kind of simplifying it. The graph of f has a vertical asymptote at each real zero of q of x, so that's our denominator. So remember, anytime our fraction is undefined, that gives us asymptotes. And things become undefined when you have a 0 in the denominator. So vertical asymptotes come from our denominator equal to 0. We have at most one horizontal asymptote. And with horizontal asymptotes, let's add a couple things in here. With vertical, we never cross. With horizontal, we can cross sometimes. So not always, but sometimes we'll cross them. And the horizontal asymptotes we get from looking at the degrees. So first I want you to think about these rational functions that we did, ones where we had a constant in the numerator and x in our denominator. We found that those had an asymptote of y equals 0 every single time, unless there was a number outside that shifted it, but it was y equals 0. So that's actually our first case here, where it says m is less than n. So what that's looking at is that's talking about our degrees, and that's saying the degree on the top is smaller than the degree on the bottom. And by degree, we mean like x squared. If a polynomial starts with an x squared, that's a second degree polynomial. So we're looking at degrees. So this one, I had a constant in the numerator, but x is to the first power in the denominator, so it was bigger degree on the bottom. So if we have a bigger degree on the bottom, just like we were doing in 8.2, that's when we have a y equals 0. And I think it's easier to think about bigger degree on the bottom than these m's and n's and trying to remember which is which. So y equals 0. If our degrees are the same, and that's going to be like that second kind of rational function that we looked at in 8.2. So let's go ahead and scroll up. So those were linear in the top and bottom, but more importantly, the degrees were the same. What we did is we took the coefficients, those leading coefficients, and we made a fraction out of them. And so we said like y equals 1 over 1, which is just 1. So it's the same thing now today. It doesn't matter if it's a higher degree, if it's squared or cubed or whatever it is, as long as the degrees are the same, we're going to make a fraction out of the coefficients. So this is fraction out of leading coefficients. So this is all in that middle box. So those two are kind of just continuations of stuff we've already done. So the last one is when we have a bigger degree on the top. So bigger degree on top is the weird one. So we know that the end behavior is going to have this, and we're not going to worry about that a whole lot this year, but they show taking your leading coefficients, making a fraction, and then subtracting your degree. So that tells you your end behavior, and that there's no horizontal, but there is a slant if 1 degree bigger. And that's the special case we're going to be looking at more this year. So we have this thing about end behavior that's kind of useful, but we're not using it a whole lot. But the slant, it's going to be a slant asymptote of 1 degree bigger. We say slant because it's not a horizontal line, it's a slanted line. It could go up, it could go down, but it's not horizontal or vertical. It's a slanted line. And that's if it's 1 degree bigger. And you get that by doing your numerator divided by your denominator, and then just using the linear part of that. And we will definitely look at one of those examples. So if it's bigger on top, there's no horizontal, but there can be a slant if it's 1 degree bigger, and we know some stuff about the end behavior that will become a bigger deal later on in math. So looking at our first example, we're going to actually try all this stuff out. We're always going to look at our asymptotes, and we're always going to look at our intercepts. So just like before, we're going to do 4 steps when we're graphing. So to get my asymptotes for my vertical or my x asymptotes, I need to take my denominator and I need to set that to equal, because when it is undefined, when a fraction's undefined, that's when I get vertical asymptotes, because those are the things that x can't equal. I get x squared equals -2. Let's see, we take a square root, and it is undefined. So, well, there's no real solution to this, and so I have none. So there's going to be no vertical asymptotes. So remember, those are always denominator equal to 0. When I'm looking for my y asymptote, that's the tricky one. That's when I'm looking at those degrees. And my degree is bigger on the bottom. And if my degree is bigger on the bottom, that means that I automatically have y equals 0. So I'm going to go ahead and dot that line in. And I know it's kind of right on that x-axis. It's tricky to draw, but it's really helpful when we're graphing to be able to actually look at that. So then I want to look at intercepts. So I got my x asymptote by doing my denominator equal to 0, and I didn't actually write that part, so I want to add that in. We try to be really descriptive in our notes so we know what's going on later on. So for my x-intercept, I want to have my numerator equal 0. So if I have 0 divided by anything, it equals 0. You have an x-intercept when your y is 0, so it makes sense. So if I make -2 equal to 0, that is a problem. It's not going to happen, right? So there's none. I have no x-intercepts. All right, for my y-intercept, I am going to let x equal 0 and simplify. And I say simplify because y is already by itself. I don't have to solve for it. So that means y is going to equal -2 over 0 squared plus 2. So that's just going to be a -2 over 2, which equals -1. So my asymptotes, I write as equations because they're lines, but my intercepts, I need to write as ordered pairs. Since I put in 0 for x and I got -1 out for y, it's 0, -1. So these are those 4 things I'm always checking before you graph. I'm looking for your asymptotes and your intercepts, both x and y. So there's 4 graphing things we're going to do before we graphing. Sometimes we might have to do some extra steps, but this is always our minimum. So I want to graph the 0, -1. So when drawing this graph, I always like to show students the wrong way before I show them the right way. So I would draw something like this, and I would say, well, why can't I do that? And then in variable, they'll tell me, we don't have any x-intercepts, so we can't actually cross the x asymptote. And that's exactly the right answer on that. And then maybe I would draw something like this. And then they would remind me that our graph has to go towards the asymptotes and not away from it. So there's really only one way to draw this graph. I need to make it kind of go smooth towards those asymptotes. This is a really crummy graph because it's small and I'm trying to draw on the screen. Oh, I just accidentally shifted my screen. Let's switch it back. Sorry about that. But it's going to go closer and closer to those asymptotes. So I'm almost making it like this shape. It's just really hard to see because I'm zoomed in super close and I'm trying to hold up my pen funny while I'm graphing. But that's the kind of shape that we're looking at. So because we can only cross that y-intercept right there, we can't cross the x. We've got to get closer and closer to the asymptotes. That's what asymptotes do. That's really the only shape of the graph we can draw. So our goal on these is really to do as little as possible when we're graphing. We really want to just make kind of a general guesstimate about the way the graph looks, but we're not making a blind guess, right? We're basing our guess on math, and our goal is to quickly graph something and move on and not have tons and tons of accurate points on them. When we do in higher math need to graph stuff like this, it's because we're thinking about how the function looks, and it's not the whole point of our math problem. We want to be able to do it quickly. So I'm going to start example 2 with asymptotes again. So for x, I am taking my denominator and I'm making it equal to 0. So that's x squared minus 4 equals 0. So we'll add 4, take a square root. We could also factor. When I have a square and a root, I have an absolute value, so don't forget about that. So my x is plus or minus 2. For my y asymptote, I need to look at the degrees, and my degrees are the same. So when my degrees are the same, I know I make a fraction out of the coefficients. So remember, I have a negative 1x squared. Normally, I wouldn't write all of this out, but we're doing notes, so we want to have something to look back on later. And then I'm going to make a big show of circling those leading coefficients and writing y equals negative 1 over 1, which means y equals negative 1. So I always want my notes to be useful later on. I want to know where I got this information from. To do our intercepts, our x-intercept is always numerator equal to 0. So that is a negative x squared equal to 0. Since it's just a monomial with x, I know that the only answer there is really x equals 0. I can just jump directly to that, which is the point 0, 0. And then for my y-intercept, I want to put a 0 in for all of the x's and then simplify. And hopefully you are not surprised to find that this is just really 0 over negative 4, which is just 0. Because I already said 0, 0 over here, didn't I? Okay, so our asymptotes are always equations. Our intercept is always an ordered pair. And then I want to go ahead and graph. And I have a negative 1 for y. My x is 2 and negative 2. I feel like if I had bigger graph paper, it might have been easier for these two. So I'm going to start in the middle because that's where my point actually is. And then because it's kind of boxed in, I've got this kind of thing going on. If I'm looking at the middle part of this graph where there's a point and it's boxed in, really the only way it makes sense is to draw this as almost like a parabola, kind of going up towards the sides there. So our graph is always split into parts based on those vertical asymptotes because we can't cross them. So I'm going to have, let's see what happens when I do a highlighter. This could be a mistake. So I'm going to have one part of my graph over here in the yellow. There's going to be one in the middle. There's going to be one over here. So I'm really going to have 3 different parts to that graph that I'm looking at. So I have just figured out what's going to go in the middle part. So I know it is going to go through this point and closer to my asymptotes. So on the left, I don't really know what's going to happen. So I might make a test point. And my test point can be any x value in that region. So the line's at negative 2. I don't want to plug in negative 2, but maybe I use x equals negative 3. So let's see what happens at that point. Sometimes I use a specific point. Sometimes I just think about whether this is going to be negative or positive. But since my line's at negative 1, I don't know if that'll be as useful. So my numerator will end up being a negative 9. My denominator is a 9 minus 4. That's just 5. So I have negative 1 and something. So I know it's going to be over negative 1. So that means I'm going to get a point down here somewhere. And all I really need is 1 point then to know what my graph looks like. Because whenever I have those 2 lines like that, I've got kind of that L-shaped graph going on. So you're going to see those with rational functions a lot, especially with our end behavior. Like as x goes to infinity, as x goes to negative infinity, we're going to see those graphs. So now I want to think about what if I put in a positive 3? But it turns out if I put a positive 3 in, the same thing's going to happen, right? I still have this minus on the outside. My denominator is still going to be positive, and I'm going to end up with a negative. So I'm going to draw a similar kind of L shape on the other side. That one looks a little bit prettier. And I'm done with my graph. So notice I didn't actually plot the point negative 3 comma negative 9/5. I'm not worried about that. I'm just trying to figure out like where those parts of my graph go. So on our last example, we have one now. I've got an x squared in the numerator and just an x in the denominator. So you knew that we were going to have to look at all those kinds of degree scenarios. So asymptotes again, my x asymptotes are going to come from my denominator equals 0. And I'm still writing down those work steps so that if I was to look back at my notes, it'd be really clear where that came from. And then I solve for x equals negative 2. My y-asymptote is definitely trickier this time. It's bigger on the top, and if it's 1 degree bigger, that would mean slant. Otherwise, I just worry about end behavior, and it is 1 degree bigger on top. 1 degree bigger on top. So what I'm going to do is my numerator divided by my denominator to get the slant. So the way I do that is my numerator is x squared minus 2x plus 1. Again, I'm showing a lot of work here just because these are notes and we're dividing by x plus 2. So I'm going to take my numerator and I'm going to use synthetic for this. I could use long division, but I really want to use synthetic. So this is a 1, negative 2, 1. And because it says x plus 2, I'm really using a negative 2 here. Bring down the 1. So we're always bringing down the first number, and then we're going to start that multiplying and adding pattern. So 1 times negative 2 is a negative 2, and then I add. Negative 2 plus negative 2 is negative 4, and then I multiply. Negative 4 times negative 2 is a positive 8, and then I add. And then I want to think about how I would make this back into some kind of polynomial. Because I started out with an x squared, this is now an x, and this is my constant term, and then the 9 is my remainder. And in order to make this into an equation for my slant asymptote, I'm actually just going to reject the remainder and write y equals. And now I have my slant asymptote. So I did not use the remainder for anything. The rest of that when I divided gave me something that's linear, and that's going to be my slant. So now I still need to do my intercepts, and hopefully I have enough space for it here. So intercepts for x comes from the numerator. So numerator equals 0. So I have x squared minus 2x plus 1 equals 0. So I can factor this. So because it's x squared, I know there's 2 answers, but because it's a perfect square, my answers happen to be the same, right? That's a repeated solution. So x equals 1. And again, that's going to be 1 comma 0. And then I need to figure out my y-intercept. I think I'm going to have to put that one over here. We're kind of running out of space. So my y-intercept comes from letting all of my x's equal 0 and then simplify. Okay, so this is for y. So then y is going to equal 0 squared minus 2 times 0 plus 1 over 0 plus 2. So all of these zeros are pretty much just gone. I have y equals a 1/2. And that is a 0 comma 1/2. So remember, my intercepts are ordered pairs and my asymptotes are equations. Okay, so let's go ahead and put all this together. So I need to write, let's see, I have an asymptote at negative 2. Seems like every year students are really confused about how to graph that slant asymptote. It's just really a y equals mx plus b. My y-intercept is negative 4. My slope is 1 over 1. So we're just really going back to linear stuff. 1, 2, 3, 4. Let me double check that. So there's my y-intercept for this line, right? Not this y-intercept, the one for this line. And then my slope is up 1 over 1. So I'm actually going to kind of space these kind of far apart because up 2 over 2 or up 3 over 3 is the same. And I'm just trying to get, oh shoot, I made that not a dotted line. I'm just trying to not gunk up this line too much because I'm going to be making some points for my intercepts also. Okay, so my x-intercept, I have 1 at 1, 0, so that's a point, and at 0, 1/2, so that's a point. So when I'm looking at those 2 points, I know that one is kind of up above the other. So it's not going to make sense, especially with those asymptotes like this, to go like that and connect them, right? That would cross my intercepts. It doesn't make sense. So instead, it's really going to kind of curve the other way. So when I draw that part of my graph, I'm going to draw it like this. And then hopefully you've noticed with these rational functions that every time I have any kind of like x with my asymptotes, that those rational function parts are always across from each other, right? They're never next to each other. We could find some that are next to each other if we worked really hard and we used absolute values or we had other weird stuff. But for what we're doing right now, they're always going to be across from each other. So that means I am going to go ahead and draw this part of my graph in. And I already know where that part is. So I don't even have to do any test points. I could completely do a test point if I wanted to. I could maybe plug in x equals -3 or -4 and do that, but it is not necessary. We're just trying to get a general feel for where the graph is. 8.3 is usually one of the most difficult sections in this chapter. I would encourage you to just keep practicing. You'll find on each homework assignment, there really aren't that many of these problems that you have to graph. So the ones that we're asking you to graph, we really want you to put some effort in. If you need to do test points, that's fine. As long as you are showing your teacher those 4 steps for the asymptotes and the intercepts, we'll have something to help you with. We can help you figure out how to connect the graph in there. We just really want to make sure that you're putting that effort in. So please ask for help in class, and good luck working on 8.3.